Well, as many others, I want to start with thanking Dan, whom I can see here, and Ben, and Moray, whom I don't see, for having me here. This is a fantastic opportunity to come here. It's always a great place here in Cambridge, and this is especially a nice mixture, I thought. Many exciting, interesting talks. I will also tell you a story about cold atoms in optical cavities that we've gone through during the past few years. And I want to begin to show you my collaborators. Basically, there's as an important part of theory support by these four fellows from Hamburg, Ludwig, Reza, Michael, and Prasanna from Innsbruck. And we have an experimental team, obviously, with two teams of PhD students, the old team and the new team. These two guys are the old team, they're now graduated. This is the new team, and they're in the phase of learning. Well, soon, hopefully, sort of take over. So this is my outline. I will basically show you different aspects of a system consisting of BC inside a standing wave cavity, and it will turn out that, depending on the way how light is coupled to this cavity, fairly different physics arises. This is sort of my order principle for this talk. So you see there are different kinds of coupling that you can choose, and depending on that, I will show you different aspects of the physics that you encounter. Recoil resolved cavity-assisted scattering. We have looked at in situ Bloch oscillation detection in this scheme here. If you have a single-sided transverse coupling, there's physics that sort of connects to metawave superradiance, as it has been looked at in an old experiment by Wolfgang Ketterle. And well, in that case, we are into the extended open decay model, and I will show you how we can do quenches across the phase boundary and what happens then. And also at larger lattice depth, one can sort of combine the Hubbard model with the decay model, in the sense that self-organized mod insulator can be put together. And well, I close then with telling you also in one slide, I think, what happens if you work with unbalanced coupling. And there's a crossover between quite different kind of physics, metawave superradiance and self-organized self-organization phase transition. Okay, this is the cavity that we have in Hamburg, and the main point, apart from the fact that it has a high finesse, the main point is that it has a length of 5 centimeters, which means that at a finesse of 340,000, the cavity bandwidth is in the kilohertz regime. Right? That makes it pretty different from all other cavities I know. In one sense, it adds some interest. In another sense, it makes it hard to operate because your laser has to be well behaved to talk to this cavity. Okay, so we are strongly coupled, as I'm showing you here, and to be strongly coupled, we need something like several 10,000 rubidium atoms in our BC. So these are the 4 coupling scenarios I will discuss: axial coupling, transverse traveling wave, transverse standing wave, and transverse unbalanced. Now let's go to axial coupling. This is kind of the most elementary way of thinking about a cavity. Everybody has seen something like that at some point. We couple the cavity through a laser, through one of the mirrors, and well, our cavity is recoil selective. The recoil frequency is 3 point something kilohertz, and that well, compares with the cavity bandwidth of 4.5 kilohertz. So it's important to well, sort of draw these different kind of momentum states. This is where the BC is prepared, zero momentum, and scattering photons from the atoms will populate these discrete momentum states. And here I'm plotting basically the elementary processes that can happen, starting with the BC at zero momentum. You can shine in a photon here, which is blue detuned with respect to the cavity resonance, and well, you transfer your BC to this momentum state, usually to both momentum states. And yeah, if you do that, then after that has happened, after the atoms appear in the plus minus 2h by k states, nothing more can happen because the cavity bandwidth, which is indicated by this gray bar, is so small that processes that take more than 4 recoil energies, which is the energy distance from here to here, like this process that takes 12 recoil energies to go from here to here, it cannot happen. So there's a, if you want, a sort of a scattering blockade. Every atom can scatter a single photon, and then the cavity takes it out of resonance for further scattering. Okay, and in the same way, you can imagine a situation when your BC is prepared at these two states, then by having a red detuned photon impinging on the BC, you see that you can transfer the atoms back in the zero momentum state and sort of recover UBC. The process that these kind of scattering processes I'm talking about, they are super radiant in the sense that I want to explain to you in this figure. Like if you start and you couple an accelerator to the cavity, there's a standing wave, the atomic density is flat to begin with, and this is, if you want, the momentum spectrum. And then a little bit of backscattering can occur, despite the fact that this density distribution is homogeneous. There's always fluctuations, quantum and thermal, and then the plus minus 2h by k states become occupied, and that leads to a little bit of a lattice commensurate modulation. And as soon as that is there, then scattering is constructive from every lattice side, and kind of in an exponential way, there's a pulse of light appearing in the cavity. And well, that can go on. More and more atoms appear in this structured distribution, but at some point, if you cross this situation when half the atoms are in the plus minus 2h by k states, then you see that second peak comes up here. And at the end, if everybody is in plus minus 2h by k, you see that again the distribution has come to life that is not superradiant, that terminates that emission. So that shows you that what you have to expect is that there's a pulse of light interacting with the atom, and after that it's done. And this is how it looks in detail. Let's look at these two graphs first. I'm showing you here the time that we've switched on the Exo Coupling. And at the beginning, there's no lattice inside the cavity. And then what you see is there's a small time period where things are oscillating, and then sort of a steady state level of light is produced in the cavity. And what's happening here is basically that in the beginning you have processes like that where you excite the atoms with the frequency omega p, and a longer wavelength photon is emitted into the cavity to transfer the atoms from here to here. And obviously now we have photons, two frequencies that make a beat, and this is the beat between the frequency that's emitted into the cavity and the frequency that you offer through your Exo coupling beam. And once everybody is, all the atoms are in these two states. This kind of process is not happening anymore, as I was showing you before, and there's a constant level of light, a lattice of a certain depth in the cavity. Things remain stationary. And well, you can do that for different pump strengths, and then you see curves like that. This is at this strength here, or this curve at that strength. And you see these oscillations that at some point terminate, and here's the steady state. And this is a mean field calculation that basically shows the main features of this process. Okay, I also want to show you that. This is already a few years ago. If you apply such pulses, as I was showing you, you get this kind of beating, and the atoms are transferred from zero momentum to plus minus 2h per k. If you take a momentum picture after this has happened, this is how it looks. And then here we have subsequently applied a ready-tuned pulse. So now we're doing what's depicted in this detail here. We have a ready-tuned photon, and we are recombining the atoms back in the BEC. And this is that second pulse that is applied here. Now, as I told you in my introduction, we have looked at in situ monitoring of Bloch oscillations using the cavity to get sort of a non-destructive method at hand to detect Bloch oscillations. This is a typical Bloch oscillation signal that many people produce in optical lattices. And what we can do is we can look at the light transmitted through cavity, that's this blue curve here, and we see that the same oscillation, the same frequency shows up in the light transmitted through the cavity. Why is that interesting? Well, Bloch oscillations are used by people doing precision metrology, for instance, measuring little g, acceleration sensing. And if you want to do that very precise, you need high data acquisition speed, and that's hard to do because in a curve like that, for every point you have to cook a new BC. So that's time consuming. If you can look at such an oscillation, which comes from a single point here, you have gained a lot of time. And so that's good for the metrologists. And then a question arises, well, first, why is that so? Why is there an oscillation in the intercavity lattice depths? And that is very easy to understand. A Bloch oscillation means that we are traveling with our wave packet through the Brilliant zone. If we start here, our Bloch function will have basically a large constant contribution and a little bit of lattice commensurate wiggle on top. And as you drive up here, the contrast of this lattice commensurate wiggle gets larger and larger. At the end, it has standing wave character. If you're at the end of the Brilliant zone, that corresponds to the fact that this is where Bragg scattering occurs, right? And now you see that these different ways of how the Bloch function looks like leads to different strengths in the coupling of the photons. So this density distribution obviously couples stronger than this density distribution, and because of that, the line profile of the cavity shifts as the atoms move through the Brilliant zone. And if you put your coupling laser at some point, like for instance ready-tuned where this bar is indicating, then you see that you're sort of in an oscillating way drive into resonance and out. And that gives you your intercavity lattice that oscillates. Well, an important question that comes along with all that is the question of whether the Bloch frequency depends on all these cavity parameters, and there's a theory predicting that this is not the case, and this is why we've taken a little bit of a look at how that is, and this is just basically different measurements showing you that the Bloch frequency, which is plotted here in the y-axis, does not depend on all these typical parameters that you like to if you play with your cavity, like number of atoms, which corresponds to the cavity resonance shift or the strength of the coupling, or the effective detuning of your light beam that you couple to the cavity, or the number of intracavity photons. Question of how deep you make your lattice to do that. So everything looks like that's a method that not us, but other people doing metrology might want to use. Okay, so now we come to transverse traveling wave coupling. So we have a single beam coming from the left, and yeah, that may remind you of an experiment by Wolfgang Ketterle some time ago, I think 1999, yes, where he has been just shining light from the side on a cigar-shaped Bose condensate, so no cavity there, and that was enough to see these kind of pictures in momentum space due to the fact that scattering processes of this kind here form a lattice along this direction that interferes with the incoming light beam. The lattice that forms is shifted in frequency due to the recoil that's emitted. So it's a moving grading, moving density grading arising. So there's from this moving density grading fulfills the Bragg condition for efficient scattering into on the axis of this Bose condensate. There's this kind of a superradiant pulse that is emitted into the BEC, on axis of the BEC, and then all these different kind of momentum states are occupied. This is the experimental picture that they were seeing. And now if you just put a cavity around your BEC in that situation, that's basically what I've been plotting here. And well, again, you have to consider the different kind of momentum states that can be reached by scattering processes. Well, scattering photons from the incoming beam here into the cavity, and you see that it's the momentum states of the right half plane due to the fact that we don't have any beam incoupled coming from this side. Now, one point that's important here is that these different kind of scattering processes going from here to here or from here to here, that take different amounts of energy to be transferred to the atoms. And as I told you, our cavity is recoil resolved, so it makes a difference whether the energy transfer needed is 2E recoil or 6E recoil. We can dial that in by tuning the frequency of the photons coming in. So we can put the frequency such that only the 2E recoil process is happening. Or if we have atoms to start with at the 2-0 mode, then we could dial in the 6E recoil process to bring the atoms from here to here. And I will show you how this works. So concentrating for a second on the 2E recoil process, so this would be the process where either of these scatter and transfers happen here along these two possible passes. And well, important point once again is to see that this momentum transfer occurs in a superradiant fashion, and well, this is basically seen if you start here at 0 with the BEC. This corresponds, the BEC corresponds to homogeneous distribution of the density. Once you populate the 1-1 state or the 1-1 state a little bit, a moving lattice arises, a lattice that is fulfilling the Bragg condition for further scattering. So this lattice is exactly what you need to have scattering consecutively interfering for every lattice site. And this lattice moves the velocity h by k over n. And once you push all the atoms here, going further on, further scattering, then again you are in a homogeneous distribution, and the process sort of terminates, self-terminates. So this should happen in a short superradiant pulse. Before I show you such scattering pulses, I very briefly want to discuss how you can sort of understand what will happen here. This is the stability analysis where simply the equations of motion have been linearized around the solution where no scattering occurs. And what you see is the system is unstable everywhere. What is plotted here is basically the excitation rate that you can calculate. So the further you go to the right, the faster the system wants to leave the state where no photons have been emitted into the cavity. And you see that the potential surfaces here, they look like, if you want, parabolas more or less tilted by 90 degrees. And the cusp of this parabolas is exactly at 2 Eureka. So the system is most unstable if you apply light that exactly lets you go from the 0 momentum mode to the 2 h/k momentum mode. That's not surprising. Maybe. Now this is a dynamic assimilation where we simply ramp up the intensity of our pump beam in 5 milliseconds from some value, well, from 0 to some value of 3 recoil. And you see that along one of those potential surfaces, the scattering occurs here in a short pulse. So what's plotted here is the number of photons seen in the cavity. And this is the experimental observation for that. Okay, so now just to show you an example, if you shine in light that satisfies a resonance condition for the 2 Eureka process, starting with BC in the 0, 0 state, this is what happens here. In the cavity, this is time axis. When we ramp up the strength of that beam, this is the reddish line, indicates ramping up incoming light intensity. And you see that basically nothing's happening until this instant of time. At the time instance 1 and 2, you see the BC is still there, nothing happened. Here, there's a spike of light emitted into the cavity, and as you see, this leads to this process happening here, and once, like at 4 here, you're already in this situation. Nearly everything has been pumped to the 2, 0 state, and after that, nothing was happening. The BC remains in the 2 h/k state. So that's dialing in the 2 Eureka process. You can dial in other processes like tuning your system to resonate with the 6 Eureka processes, these blue errors. Well, definitely since the BC initially is in the 0, 0 state, it is the 2 Eureka process that has to happen first. So you have to wait a little bit of time. It takes longer for that to happen, but eventually it happens. You see it here. This happens here at 3 in this red area. So atoms are transferred to these states and further on to that state. However, this cannot fully sort of come to an end as it did in what I was showing you before. But before this process ends, it is terminated by the fact that resonantly the 6 Eureka process sets in, and it empties these states. And emptying these states means that the grading that makes the 2 Eureka process a superradiant is terminated by the next process. So the 6 Eureka process kills the 2 Eureka process, and this is why a good amount of atoms remain in the 0 order at the 0, 0 momentum state. And so then we are populating these 2 states. Half of the atoms remain here, the other half goes here after some time. And if you wait, then higher order processes set in, and you can populate higher momentum state. That depends on how you set your detuning in detail. Okay, this is just to illustrate that there's control in all this. well, a game that we've played to make a super-ended atom accelerator, starting with the atoms in the 0-0 state, and then, well, first dialing in the two-Eureka process, going here, and so on. You can do that forever. However, you have a trap, and at some point the atom's rolling up your potential in the trap, and that terminates that. So you see what you have to do to go from here to here to here to here. You have to adjust your detuning to make it well, resonant to the process that you want to happen. So we start with this process here, then the detuning is changed to be resonant with this process, and so on. And you see each time you do that, a spike of light is emitted in the cavity to do this transfer. Okay. Yeah, here you can see that we should end up with 10 H bar K, but we're only ending up with 7 point something. This is due to the trap. Okay, so now let's go to the transverse standing wave coupling, and a lot has been said about that by many people. I'm not able to note all the people who've contributed here, especially in the theory side. There are many interesting theory papers about the system. Yeah, in this case, you have heard already a few times that there's a self-organization transition, and in some parameter space, this is sort of a simulation or an emulation, if you want, of the open Dicker model, closer to the self-organization phase transition. And how does that come about? Well, if you have two lasers from both sides, a standing wave, then now you have the full 2D momentum plane at hand. All these states can be, in principle, contributing. And you see that now there's something new becoming possible. Again, if you shine in photons that are blue detuned with respect to the cavity resonance, you can excite your system in the way I've shown you for the case of a single beam. This would be this kind of processes bring the atoms up here. But now if you shine in a red detuned beam, there's a possibility of going down into the sort of red region of this diagram, and well, the fact that now you can build up a stationary lattice, this lattice that you build up here is no longer traveling but stationary. You can get the stationary state that you can pump your atoms into. And once the atoms are down here in your self-organized lattice in the lowest band, then these processes that take you down there don't have to happen anymore, they terminate, and you have a stationary state where photons scatter back and forward and maintain your lattice. Okay? So just, well, very briefly, since you've seen all that, this is how the self-organization transition basically occurs. You start with the situation intensity of these incoupled beams is low. In that case, you just have a standing wave along this axis. The position of the atoms along the vertical axis is arbitrary at a certain strength. Scattering sets in, and the interference between the standing wave being built up in the cavity and the one that you have externally applied leads to this kind of checkerboard type lattice. And this is sort of associated with a homogeneous atomic density along the cavity axis, while here you have a stationary intercavity optical lattice. From the many-body perspective, you can say that, and this has been talked about already, that photons mediate a long-range interaction between the atoms. In our case, this is the same as well. However, we have a retarded interaction. The fact that the evolution of the matter variables and the light variables happen in the same time scale means that you cannot integrate out the light field, and due to that there's a retardation in the interaction between atoms at different places in the cavity. Okay, this is a linearization analysis, a stability analysis, where the system is linearized around what I've called here NSF, a normal superfluid mode. So no scattering yet. The atoms are in the initial BEC. This is giving you, this analysis gives you the Dicke equilibrium phase boundary, and you see that all this Dicke physics happens on the left side from the zero here. So this is at red detuning, whereas at blue detuning you remain in the situation now where the system is everywhere unstable, and you basically have the same kind of physics that I was telling you before for a single beam. So here you expect a superradiance instability as before, spikes of light being emitted into the cavity, while here a stationary lattice occurs. And this is also seen in an experiment. Now the colors are fairly similar, but I'm plotting here something else. This is the intercavity photon number that you see. This is our Dicke equilibrium phase boundary here, and you see that well, this is measured in a way that the pump strength is ramped up linearly here in time in 10 milliseconds. So what you see here is typically pump strength is increased, you cross the Dicke equilibrium phase boundary, you go further in, and then it happens here at a little later than you would expect if this was equilibrium physics. On the other hand, at blue detuning, exactly what you expect happens. You see that there's on one of those equipotential surfaces here the superradiant emission of a spike of light occurs. These are these points here. You can also see that if you look at the momentum spectrum at this specific point, you see exactly what happens if you look at matter wave superradiance, the kind of pictures I've shown you before. You excite the system into the plus minus 2 HVK states, whereas if you're on the left side, red detuning, you're creating a stable stationary lattice. Now, what we've done here is to look a little more in detail into how the phase transition is traversed here. So now we are just going in and out, and the kind of observations that you find is shown here. The blue curve is the going in curve. You see that here we are crossing the equilibrium phase transition boundary here, going much further in before the system then sort of realizes, oh, I'm deep in the Dicke phase, I have to adjust, and here it does that. On the way back, it's different. You see that smoothly the system goes back into the normal phase, if you want. And these are momentum pictures along this trajectory. So you see at point A, when we are long behind the Dicke equilibrium phase transition, this is an A, we still have just the BC and the momentum peaks are coming up in the applied standing wave. And on the way back, you see that eventually the Bose-Einstein condensate that we started with at E is sort of regained here with a few excitations on top. This is not quite the Bose condensate that we started with. You see there are some phase fluctuations. Okay, so what we can do and have done is to calculate such experimental traces by, a mean field model, basically using Karl equations. And by doing that, we can sort of calculate these 2 points. This point where the system comes back down to the normal phase, and this point where the system adjusts to the Dicke phase. And now you can cross the phase boundary with different speed, and you can plot these values of the pump lattice depth, these critical values, against the speed of your quench. And well, what we've done here is to do that with the calculation first. So using these calculations that are matched to the observations, then take out from the calculation these specific values of the pump strengths, and then look at what the calculation predicts with respect to its dependence on the quench time. And you see that there's a power law behavior with respect to the quench time, and from that, these kind of calculations, we get the exponents of this power law, and then we simply plot these exponents into our data. And we see that it fits kind of okay. It's not so okay anymore on the way out, because here we're starting to lose atoms. So then the agreement is not so good anymore. And from that, and I want to be fairly short on that because my time is probably running. Actually, I should take a look. Yes, my time is running. So I want to be very short on that. This can be used to discuss this in terms of a Kibble-Zero scenario, and from the exponents that we extracted here, one of the Kibble-Zero exponents can be extracted. And at the end, that's the outcome, 0.75 on that side of the phase transition in the normal phase, and 0.18 on the other side. So they're different, these exponents, depending on which side of the phase transition you are. Very briefly, I want to show you that in the self-organized lattice, you can look at Bloch oscillations. Since we had been looking at Bloch oscillations in the axially coupled lattice, it's not too far-fetched to see whether this can be done in self-organized lattice as well. And this just shows you, yes, it can be done, but there's a lot of decoherence and heating, unfortunately, if we do that in the self-organized lattice. So what you see here is basically that we start with the BC in the Dicker phase, and then apply a force via some magnetic gradient, and you see how the BC at the gamma point is now doing a Bloch oscillation here. These are the higher order Bragg peaks, and this is exactly what's seen in the data. Finally, how much time actually do I really have? Is anybody controlling my time? 1 minute. Okay. So I'm sorry for that. I have to be quick. We can also apply an external lattice in addition to the self-organized lattice, such that once the lattice in the cavity self-organizes, the outcome is a 3D lattice, which is deep enough such that a Mott insulator arises. And this is shown here. We've been going at several detunings into the Dicker phase, and we've seen that at certain points the coherence very rapidly drops. When we go out again, we can basically recover the BC. This is seen in one example. This is this curve here. You see what happens here. Here we cross the Dicker phase transition. Light emerges in the cavity. However, the coherence is very nicely preserved. Only at a later instance here at this point along this trajectory, all of a sudden you see that the coherence disappears. And if you go out again, you see the coherence reappears first, and then you leave your Dicker phase. And that lets you plot this line, telling you that across the line here you're in a self-organized Mott insulator, and here you have superfluidity. Okay, so now I have one transparency left. This is, so I make it in half a minute. So now the question arises, how about crossing from bidirectional to unidirectional pumping? So going from this situation here to this situation, how do these two worlds connect? And I'm showing you what happens here. This is starting with the conventional bidirectional pumping And you see, as you weaken one of the beams, the area where the decay phase exists, where the lattice, stationary lattice, arises in the cavity, it moves up. So at the end, if there's nearly no beam from one side, there's still a little bit of an island where there's a decay phase. And what I find particularly interesting is that you see there's a minimum detuning, a minimum negative detuning that you need for a decay phase to arise at all. The calculations show that, but I don't have an intuitive, unfortunately, an intuitive explanation for that and what this minimum detuning really is. Okay, so then I'm at the end. I was asked to say something about the future. That's hard, but nevertheless, what I think for the future is most attractive, but that's a personal view, is to explore the true quantum regime. All this physics is, apart from the Mott insulator, if you want, but most of that physics is not really quantum physics. It's wave mechanics, if you want. It's interesting, but it's not the kind of full quantum regime that you could dream of accessing with these systems. That's something we want to do now, and we are already in deep trouble. I don't have any results on that to show. It's much harder than what we've done so far. So first, we are now into strong coupling for much fewer atoms, not 100,000 or 50,000, but 40 or 50 atoms. And then we want to study entanglement between the light and the motion states of the BEC. One dream would be to bring the cavity to a regime where you can really monitor particle number fluctuations in the cavity transmission. This is something that Igor has mentioned. There's an old suggestion by Hemmerich and Igor in that direction. Look for squeezing maybe in the transmitted light. There's also something that Igor has proposed that one could do. Or pumping these systems with quantum light sources. What about pumping the system with a squeezed beam? That could be interesting. And since we have now the world champion of squeezing, Roman Schnabel, in our institute, he has already promised to make a squeezed source for us. Okay, that's it. Summary is not necessary. It's the same as my introduction, and that's it from my side.
For the first experiment that you showed on cavity cooling, I was wondering what would happen, or if you maybe tried someone to do it with a thermal cloud, and then possibly even like chirp pulses that would narrow down the momentum distribution in one direction?
Yeah, we have obviously tried to do that. That doesn't work well in our experiment. In our experiment, there's a few drawbacks for these kind of things. One is the exceptionally high density that we have. We've squeezed our BC in a fairly elongated cigar to have it nicely in the mode. So the radius is 3 microns, and we have on around 4 times 10 to the 14 atoms per centimeter cube. We need the atoms to be strongly coupled. So we cannot say, okay, let's go down to a factor 10 less atoms, then we cannot work, not in a strong coupling regime. So that's something that makes these kind of things a lot more difficult. But you see a little bit of, you can push things a little bit together, but it's not fantastic. We've not even published it because it would not be, but if I'd see that data or somebody else published that, I say, this you cannot use.
But if one, in principle, one could definitely, well, change things in our apparatus and demonstrate that.
We only have time for one more question, but you can ask it during the topic.
Okay, I'll ask the question. So in the data on block oscillations, I can buy the idea that the block oscillation frequency is independent of what's going on. But of course, the signal ought to be distorted, partly because of retardation, partly because of. Anyhow, can you explain like the actual non-sinusoidal block oscillation signal coming out of the cavity?
Yes. Yeah, there is, well, we've looked at the FFTs of the oscillation and see that there's higher harmonics. But even without the cavity, you expect that to happen if you have a shallow lattice versus a deep lattice. Like in a shallow lattice, you have higher order contributions from the fact that your Bloch oscillation is basically, mostly you have kind of a linear acceleration and then a very instantaneous Bragg scattering process. So you have these kind of ramp-like like if you look at the conventional signal from Bloch oscillation, then well, this is not a symmetric signal. Here the way it's the way the analysis is made here, the ramp is here basically infinitely steep because we have just taken the maximum of the. But you can take the average and then you still end up with an asymmetric signal depending on the depth of your lattice.
Right, but I see also the Bragg signal that you get is pretty asynchronous to the.
Oh yeah, there's a phase delay. That phase delay is reflecting the delay we have in the system. Yeah, that's exactly where you see that the matter variables they don't follow the light instantaneously. And that has been we have Prasanna Venkatesh has made calculations that show that.
And they kind of reproduce this waveform?
Yeah, they kind of reproduce that. I mean, this is not the kind of reproduction where you want to put one curve across the other, right? Yes. But the features you see. I have only very few data here. Like this is, you see, this is experimental data for different detunings, blue detuning and red detuning. You see that for blue detuning and red detuning, according to the explanation here, you are 180 degree out of phase with the oscillations because here for the red curve you sit here with your pump laser and you see that the motion of your the cavity profile is out of phase by 180 degree as compared to the case when you sit here. Right? And this is the calculation along with that. And you also see here that you see that high harmonics are getting important here, and you can sort of, well, dream that this is not completely.
Okay, let's thank the speaker again. Our next speaker is Jonathan Simon from University of Chicago.
You got an hour and a half, right?
Yes.
Yes? Perfect.
First half of which you're speaking, and the other half of which you're sitting.
Okay, great. Well, there's the Thank you very much. Okay,
You are next one.
yeah. I do need to wear this? I see, that's for those guys. Great. Of course, I want to thank the organizers for inviting me. It's always fun to be back in the old stomping grounds. This conference has really been sort of a unique pleasure. I was chatting with Ben about this earlier. It's rare that you go to a poster session and everybody has cavities. So anyway, it's really great to be here. I'm going to tell you primarily about work going on in my group building topological matter from light, and also a little bit about some collaborations with Dave, sort of the complementary piece to what he told you about yesterday. But I thought I'd sort of front load with the vision, because if we're being realistic, I won't get to it at the end. I think one thing we've really taken away from this workshop so far is that many-body cavity QED means many different things to many different people. I think one neat avenue, and one that I'm pushing on, is making photonic analogs of condensed matter models, right? I don't think this is the only paradigm where one can explore interesting physics in sort of a many-body, strongly correlated context. But that's the one that we're focused on in my group. And I think to some extent, one can really just ask questions about these condensed matter models in general, but I think there's also a lot to learn from the implementation process with light, as opposed to implementing with cold atoms or in a solid state, and also from the unique properties that we get from the photonic implementations. So I'm going to try something kind of new today, which is I always give this talk about, let's talk about making the ingredients for fractional quantum Hall states. And I realized that probably, at least in the cavity QED community, many people probably don't know what a fractional quantum Hall state is. I know I don't. But so what I thought I'd do is start with a quantum optometrist's view of what a fractional quantum Hall state is, and use that as kind of a leaping off point for the remainder of this story. So just by way of background, you know, the game in general that I'm focused on is you have some solid state model where you have electrons whose properties come from some lattice of ions. When I say properties, I mean their dispersion, the behaviors of the individual particles. Okay? And then entanglement and richness comes from the interactions of these electrons. So the condensed matter with ultra-cold atoms paradigm is to explore this kind of physics where the properties of atoms are determined either by lattices or other sorts of laser beams, and the richness comes from the interactions between the atoms. And so, you know, I think some of the story of this community is to say, let's control the properties of photons with some sort of metamaterials, right? Be they circuits or microwave resonator arrays, or in our case, multimode optical resonators, and then use sort of very modern quantum optics tools to allow the photons to interact with one another. With that kind of a backdrop, that we need to engineer the single particle physics, and then we need to engineer the interactions between the particles, let's take a step back and talk about electrons initially in magnetic fields. So So this is kind of the Hamiltonian for an electron in a magnetic field, either classically or quantum mechanically. And what we know is that this electron just goes in a little cyclotron orbit. So here the magnetic field either points into or out of the page, whichever one makes it go around in that direction. I can never remember which one's my right hand, so we'll leave it at that. But we would really like to understand the quantum mechanical version of this ultimately, but I don't want to diagonalize Hamiltonians with you guys, so let's see what we can get